Hello everybody, I'm Elizegi from Mondragon Universitatea. I am currently doing my doctoral thesis about pitting in years, and in this presentation entitled Pitting Evolution in Years, I will present some partial results. Firstly, in the introduction, I will present the topic, its state of the art, and the objectives of this work. Then the theoretical and experimental procedures. Continue with the presentation of the case study and the results. And finally, I will present the conclusions and the future lights. Gears are mechanical elements widely used to transmit torque and speed as desired. Gears' most common mode of failure are tooth bending fatigue, pitting, and wear. And in this presentation, I will focus on the failure due to pitting, which is a surface fatigue failure. In surface contact fatigue, the matting surfaces are damaged due to the appearance of pits, which are crack formations due to the detachment of particles from the surface. These pits are the consequence of material fatigue resulting from a combination of contact pressure and surface sliding-induced shear stress. It is initiated when the local sliding and rolling contact stress exceed the permitted strength for the material. The failure due to the appearance of pits is known as pitting or spalling in the literature. Some researchers difference between spalling and pitting in accordance of the description shown in the upper middle figure. There are who use micropitting, pitting, and spalling to refer to different amount of removed material, and finally, there are the ones who use the terms pitting and spalling indistinctly. Normally, the pitting appears in the dead end of the gear teeth, which is the area between the reference cycle and the tooth root cycle, because in addition to support the maximum stress, in this part, the direction of the roll is opposite to the direction of frictional forces. Here, there are two examples. On the left hand, a pitting's evolution is presented at 2.5, 10, 10.76, and 10.84 million low cycles. On the right hand, a spalling on a lifting gearbox's pinion is presented. A pit was generated at lower left point, and as the gearbox kept on working, it evolutionated up to the shown spalling. Regarding gear sizing standards, ISO 6336 Part 2 and ACMA 2101 are the most used ones, and they based on comparing the permissible contact stress with the applied contact stress. According to ISO 6336 Part 2, it is pitting failure in test evaluations when the following limits are exceeded. 2% of the total working flank area of true hardening gears is damaged by pitting. 0.5% of the total working flank area of surface hardening gears is damaged by pitting. 4% of the working flank area of a single tooth is damaged by pitting. However, it is not specified the reason of this percentage of pitting to be critical. ACMA 2101 determines a lower rating at which progressive pitting of the teeth does not occur during their design life. The disadvantage is that it is difficult to know when progressive pitting starts because no reference value is given. In summary, they both insist that the level of critical pitting depends on each application, because while the consequence of pitting failure in an aircraft is very dangerous because it can put many human lives at risk, the result of pitting failure in a tractor or pond gate is nothing more than an annoyance as no human lives are put at risk. However, current sizing standards limits are the same for all applications, resulting in oversized gears in many applications, which means that their manufacturing cost is excessive because the gears do not need to be as large. There are examples in the literature at which pitting levels higher than 4% of the working flank area of a single tooth have been obtained. Fan carried out tests until having 8% of a tooth damaged by pitting, while TAN stopped the tests when the percentage of gear pitted area was 50%. In addition, Dudley mentioned that pitting levels of between 50 and 100% of tooth area are acceptable if the cost of replacement is high and they are in a forgiving environment in which noise and vibration can be tolerated, for example in some factory and farm applications. To conclude, it is known that the gears continue to work properly when pitting exceeds 4% of the working flank area of a single tooth, but there is very little information explaining its progression, which is essential in order to extend gear life. Taking into account all that, the objective of this work is to determine how much the theoretical pitting life can be extended. For that, firstly, the experimental pitting damage evolution will be analyzed, focusing on cycles after extending the pitting failure limits of the existing standards. Secondly, the difference between case studies' calculated pitting life and obtained experimental pitting life will be quantified. In this chapter, just theoretical and experimental procedures are presented. ISO 6336 Part 2 has been used to calculate the life until pitting failure. The reason for that choice is that the calculated life will be compared to experimental life, and this safety standard gives limit values of percentage of year pitted area which make easy the comparison. This standard consists on comparing the permissible contact stress of the year with the contact stress applied on it. In the experimental procedure, a back-to-back or mechanical recirculation test bank has been used, which consists on an electric motor, 2 gearboxes, a load clutch, and a torque measuring clutch. Pictures of the gear teeth have been taken during the test to measure pitting. The tooling in the figure on the top right has been used to ensure that all pictures have been taken in the same way. Then, these images have been processed in MATLAB to automatically detect the percentage of pitting, as shown in the right figures. In addition, vibrations, sound, and temperature have been measured during the test. To finish, with the experimental procedure, it is important to note that the tests have been stopped at 30 million cycles, which corresponds to approximately 10 days of non-stop testing. Spur gears with a gear ratio of 0.5 has been used, with 25 teeth in pinion and 50 teeth in the gear. Gears are made of C45 through hardening steel, a steel with very low hardness to ensure pitting appearance with little amount of cycles. FVA3 oil has been used and 2 tests have been carried out at a speed of 2000 rpm in the pinion and the lubricant at 70 degrees Celsius. The torque applied in pinion in the first test has been 112.5 Nm and in the second test 95.5 Nm. The results. In this slide, theoretical results calculated according to ISO 6336 Part 2 are presented. The pinion life of the second test is double that of the first test. The torque of the second test has been chosen specifically for this case to see if this relationship is maintained in the experimental test. Besides, all calculated lives are lower than 1 million cycles, but 30 million cycles have been performed in the experimental tests. In the following slides, experimental results are presented. Just in this slide, the pitting evolution on the critical tooth of each year of the 2 tests are presented. The horizontal orange line is the pitting failure limit of ISO 6336, and the 2 vertical lines on the left side of each graph are the calculated pitting life of the pinion and gear with ISO 6336 Part 2. In test 1, all gear's critical tooth has exceeded the limitation of 4% pitted area, and in both tests lives much more longer than calculated, which are the vertical lines, have been obtained. If we focus on the most damaged gear tooth of test 1, we can see that pitting up to 17% of working flank area has been obtained, which is quite more than ISO 336 limit of 4%. In addition, in the right side of the slide, these two photographs taken at different number of load cycles are shown. It can be seen that the evolution of the area damaged by the pitting has been quite stable, that there has been no exponential growth. In this slide, another limit of ISO 6336 has been compared. It is pitting failure when 2% of the total working flank area of through hardened gears considering all teeth is damaged by pitting. There, the same conclusions as in the previous slides has been obtained. Gears in test 1 has exceeded ISO 6336 limitation, and in both tests, lives much more longer than calculated, the vertical lines on the left side, have been obtained. In these bar diagrams, the obtained results are summarized. It can be observed that the duration of the test has been up to 150 times longer than the PT life calculated with ISO 6336 part 2, which has been graphed with dark blue bars. To finish with the experimental results, number of teeth with pitting and with more pitting than 4% of the working flank area has been graphed, the latest ones with continuous lines. Pitting in more than half of GR teeth have been obtained. Taking into account all these results, in the last chapter of the presentation, the obtained conclusions and future lines are presented. Regarding the conclusions, at the end of tests, the GRs were working properly, so pitting up to 17% on a tooth, pitting up to 9% on a whole GR, and pitting in more than half of GR teeth is not critical in the case study. In order to confirm that the GRs were working properly, vibrations, sound, and temperature have been measured during the test and no significant increase has been detected. Furthermore, it has to be mentioned that pitting has not grown exponentially. This leads to conclude that sizing standards limits are very restrictive for the case study. Additionally, it has been observed that in test 2, the pitting does not appear and progress as in test 1 but by performing twice as many cycles, despite the fact that the torque has been chosen specifically for this purpose based on the calculations. This leads to think that there is some phenomenon related to the torque that the sizing standards do not consider. In order to answer to the main objective, in this case study, GR's pitting life can be extended up to 150 times the life until pitting failure calculated with ISO 6336 part 2, so currently they are very oversized, which involves the disadvantages mentioned in the introduction of the presentation. As mentioned at the beginning, the results and conclusions presented are partial and more tests are being carried out in the doctoral thesis. In the future, it will be really interesting to continue testing until the GRs do not work properly due to pitting, in order to know the amount of pitting to be critical and consequently how much the GR pitting life can be extended. To finish the presentation, I want to thank Giulia Mascariano for helping me with the experimental part and GH cranes and components for the support received. Thank you for listening to me and goodbye.